This is a first in a series of educational videos for automotive technicians on electricity and electronics. This training is a little unique because I'm going to make use of a program called Circuit Lab. The other piece of this, which is unique, is I am not going to use a calculator or any math. The great thing about this program called Circuit Lab is it's a circuit analysis program for electricity and electronics. It does all of the math behind the scenes. I don't have to know Ohm's law. I don't have to know Kirchhoff's laws. I don't have to know any of those laws. I don't have to know the formulas. I don't have to take things and put them into a calculator because I know in real life it's not something that most technicians do. So looking at this program, I can see this first circuit that I've created. This is something called a series circuit, and it's a series circuit because all of the components, there's only one path where current can flow. If I disregard the leads of my voltmeter here, there's only one path where current can flow through this circuit. So we can imagine using something called conventional current flow. The current flows from the battery positive terminal, flows through this closed switch, flows through this ammeter. The ammeter is inserted in the circuit. Could be a Fluke 88, could be whatever multimeter that you're using. This ammeter is placed in series with the circuit. So all of the current, it becomes a part of the circuit. So all of the current must pass through this ammeter. It measures it. It tells us we got a value of 1 amp. Because there's 1 amp of current flow, I have 1 ohm resistance. Ohm's law would tell us if we were to do the calculations that that's 1 volt that's going to be dropped here. But Circuit Lab's done those calculations for us, so we don't have to do that. And like a real circuit, if I were to take the switch and I were to change the state so that it's open, now I have no current flow through the circuit, so I have basically no voltage that is dropped across this resistance. So this, if you can think of this as a light or something, when I close this switch, the light is on. When I open the switch, the light is off. Some fundamental rules to remember for series circuits. Number one, current flow is the same anywhere in a series circuit. That should seem pretty logical because if I have current that's flowing through this circuit, we'll go ahead and close the switch again. If current is flowing through the circuit, it has to be the same value of current everywhere in the circuit. So the current through the ammeter is the same as the current which is flowing through this resistor. It's the same current which leaves the battery positive. It's the same current which returns to the battery negative, once again using conventional current flow. Let's go ahead and let's put another ammeter in the circuit. And let's take a look at what that other ammeter does. So I'm going to take my ammeter, I'm going to drag it down here. We can right click on it. Let's rotate it clockwise. Let's delete this wire. Let's take the ammeter and let's drag it up here. And then let's go ahead and wire this back up. This is so much easier than with a real circuit, right? If I look at this, I have both ammeters showing 1 amp. And of course, if I open the circuit, both ammeters are going to show 0 amps. So this is our first law of a series circuit. Current is the same everywhere in a series circuit. The next rule we're going to look at, or we're going to discuss, is that the amplitude of the current flow, the level of it, how many amps it is dependent on the voltage and the resistance of this circuit. So in the series circuit, the current is dependent upon the voltage and the resistance. I can't just come over and say I'm going to change the current. It's not something that I can go into the circuit and I can change. It's a result of this voltage and this resistance. So the next law that we're going to, or rule that we're going to discuss, is that if I hold the resistance at a specific value and I change the supply voltage, so if I were to modify the supply voltage, that results in directly proportional change to the amplitude of the current flow. Well, what does that mean? Well, directly proportional means if I increase the voltage and I keep this resistance the same. So let's take this and let's change it from 1 volt to 2 volts. So let's see what happens. Well, nothing, because I don't have the switch closed. So let's close the switch. And with the switch closed, we can see that I now have 2 amps. If I were to put this back to 1 amp or to 1 volt, we put it back to 1 volt, we have 1 amp. If I change it back to 2, I now have 2 amps. I'm going to enter a value of 5 volts in it. I bet you can tell me what the value of current is going to be. It's going to be 5 amps everywhere throughout this circuit. The other thing we can see is, because this is a series circuit with only one place for the voltage to drop, all of that voltage, all of it is dropped across this 1 ohm. So let's set this back to 1 volt, and we can see that everything returns to 1. The next rule that we're going to discuss is if the supply voltage is held at a specific value, in this case 1 volt, a change in the resistance results in an inversely proportional change to the amplitude of the current flow. Well, what the heck does that mean? What that means is if I take this resistance and I make this resistance 2 amps, and when I make it 2 amps, I can see that I now have this meter show 500 milliamps. That means 500 thousandths of an amp, 1,000ths, or simple terms, half of an amp, 0.5 amps. So in this case, it's inversely proportional, correct? Because I kept the voltage at the same 1 volt value, and I doubled the value of resistance. By doubling the value of resistance, it caused more of a restriction, therefore less current flows through the circuit. The hydraulic analogy is the more I pinch something off, the less of hydraulic flow that I have. It's the same kind of analogy. The more that I close this off, I pinch it down, I restrict it, the less current I have. So let's go the other direction with this one then. Let's make it, instead of 2, let's make it 0.5 or half an ohm. And when I do that, I'm back to having 2 amps of current. Even though I've got 1 volt of potential of voltage, supply voltage, I now have 2 amps of current that flows everywhere through this series circuit. So if I put this back where we started, let's set this back to 1 ohm. If I have this back to 1 ohm, we can see we're back to 1 amp of current. Well, let's change both. What if I were to increase this to 12 volts, like a 12 volt battery? I increase it to 12 volts. I now have 12 amps of current flow. Great. What if I were to reduce this down from a 1 ohm resistor to a 12 ohm resistor? I'm back where I started. So what I've done in this case, I have increased the voltage and I have also increased the resistance. And so the end result to the current is it's back where we started at 1 amp. If I were an ammeter, I wouldn't know if anything about this circuit. I wouldn't know if I were connected to a battery of 1 volt with a resistance of 1 ohm in series, or a battery of 12 volts with 12 ohms of resistance. I wouldn't know that if it is a, we'll say, let's go bigger, let's go 120 volts, and let's set this guy to 120 ohms. This, to the amount of current that's flowing in the circuit, it's identical. Nothing has changed. The amount of current flow through the circuit is the same. Put this back to a hydraulic analogy. If I increase the pressure by a whole bunch, but I increase the resistance by a whole lot, the hydraulic flow is the same. The flow meter is going to show the same amount, and it's going to show the same amount everywhere in the circuit. And of course, once I open the switch, like an open valve, all of the hydraulic flow stops, all of the flow of electrons stop, all of the current is interrupted, and I now have no current flowing through